Welcome to Walkabout the Galaxy, the free astronomy podcast, where the science is universal, the opinions are personal, and the hosts were once again passed over for the Nobel Prizes.
Another year, another snub.
Next year, that'll be us, guys.
Yep.
They must have
our
been
mantra.
I think we might have missed a mailing or something, like a deadline.
Yeah, probably.
Yeah.
I mean, I nominated you. Did you nominate me?
Yeah, I did, but maybe I didn't put the right postage.
Oh,
so.
Maybe, yeah.
It's
confusing.
Yeah,
getting to Sweden.
and they're sticklers.
Yeah,
like he may have been the greatest, but if you didn't fill in the form exactly right, gets recycled to the next year.
Yep.
You know, we are Strange, Charmin Up the AstroQuarks, also known as Josh Caldwell,
Addie Dove,
and Hannah Sargent,
coming to you from the Walkabout studio at the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. You can contact us anytime at wtg@ucf.edu. My computer did something strange there.
And by his computer, he means his brain.
No, it was the computer.
Oh, okay.
It actually did do something strange. You can order a Walkabout t-shirt and support STEM education at the same time. Our Stumper today is Naked Eye Astronomical.
Okay.
Which rare event would you rather have happen in your lifetime? A so-called great comet, and by that I mean a daytime comet, naked eye daytime comet, or a supernova, such as, for example, Betelgeuse. Take that as an example, which would also be visible in the daytime. So, which you get, probably we're not going to get any of those, but if you could have one of those, which would you like it to be?
I want a supernova.
You want the supernova over the comet?
Yeah?
Yeah.
Why?
It feels rarer.
Yeah.
Yeah.
So.
Well, it's because we do see comets.
Yeah.
We don't see daytime comets. Like, I've never seen a daytime comet. But
even just in general, like nighttime supernova aren't.
Yeah, it's not like we see nighttime supernova really either.
Yeah,
so it's just just a completely more novel experience.
Statistically, which one is more likely? I don't know the answer to that.
That's a good question, and they may be roughly comparable. I sort of feel there have been daytime comets every sort of century or two.
Yeah.
And the
Halley's isn't, right?
It is not.
Yeah.
I
wonder if it probably was back in the day.
It could be.
If the right
depending
configuration
on,
occurred.
Sure. But no, typically they're long period comets, so we don't get advance warning of them.
Yeah.
Coming in.
They need all that fresh material to be so bright.
Yep.
I will go comet. Because I think that which one will be visible for longer?
Probably the comet.
Yeah.
And I feel like a supernova, I think I'm going to go comet.
It would depend on the orbit and everything of the comet, which one would be visible longer. Like Betelgeuse would be visible probably for weeks.
Okay.
And so,
they would both be pretty cool.
They'd both be pretty amazing. The thing is, like, the supernova will still just it'll be the brightest star you've ever seen, aside from the sun. But it's still just a point.
Sun, so it's fine.
It's still just a point of, it's just a very, very bright
I think it's something about understanding what it is more of the magic than what you see.
Yeah, it would be a point, but it would be super fascinating. And with that would be
cool.
There'd be so much data from either one of them.
Yeah. But the comet, you could, be changing its appearance over time. The supernova would just be like bright and then just gradually getting fainter and fainter.
Sure.
The comet will be moving across the sky. I mean, not...
Josh is apparently on Team Comet.
I am on Team Comet, I think, on this. I was not sure until I started talking about it. But because from day to day, it'll be in a different part of the sky.
Sure.
And
that's technically true for a supernova.
Not relative. I'm speaking in the celestial sphere frame of reference here. And the tail would be evolving and things like that. So I'm I'm definitely on Team Comet, I think.
Team Comet.
Well, today we'll talk not about comets, but
about supernova. Well,
we will talk about supernova, actually. Yeah, we will talk about supernova in the context of the earliest stars in the universe, aka Pop 3, as we like
Pop 3
to call them, and the smashing success of D.A.R.T.
It was a smashing success. I like that. Nice work there.
Thank you.
very
I was
British.
thinking of you.
I appreciate it.
I hope Hannah appreciates that. But first, this episode of Walkabout the Galaxy is brought to you by the Foucault Pendulum.
Excuse you?
Proving the rotation of the Earth since 1851, Léon Foucault's Bob on a Wire is also a handy demonstration that the Earth is a sphere. With its latitude-dependent rotation period, take a Foucault pendulum with you on your planetary explorations to determine your location. And it doubles as a handy timekeeping device. Available in lengths from 10 to 30 meters, the Foucault pendulum provides a laid-back focus for your next party or event, giving you plenty of time to ponder the connection of a simple pendulum to geometric phases and parallel transport. Custom periods are available for an additional charge. The Foucault pendulum, exact time for life.
Wow.
It's got to be like Omega or something, or like a timing system.
Like Timex.
Omega.
Timex.
It is Omega.
I thought it might. Yeah.
Well
Let's
done.
go.
Omega,
Yeah,
Omega's
you're nailing
very.
Yeah. I was surprised when I got the sponsor request from Foucault Pendulum, and I did a little background research on them. I was surprised how complicated they are.
Really?
Yes.
Are they?
Isn't
it just a string with a bob?
Well, the pendulum itself is quite simple.
Great.
Yes.
Great.
But what's going on is more complicated than my very simple-minded.
Sure.
I haven't really thought about this notion before.
Really?
Well,
we have a Foucault pendulum in the math building.
We have one here at UCF.
Yeah.
Recently restored
again,
to functional status. And there was one, I don't know if it was functional or not, but there was one at Colorado where we used to be.
I think it was functional.
In the Gamov Tower. And it's a 10-story building. It's a 10-story pendulum. The one here at UCF is like a 4 or 5-story pendulum.
Yeah, it's a big pendulum.
And the one in Colorado had a little toy at the base next to it that sort of illustrated the idea behind it. And that toy showed a globe with a fake motorized pendulum over the North Pole.
Okay.
And that gave me my simple-minded two-dimensional notion of how a Foucault pendulum works. But when you put this thing on the side of a sphere, all sorts of weird things come into play.
You can watch the little... Who resets the pegs?
Can we also, just assuming that one person here doesn't know what it is?
Well, if we were to assume such a ridiculous case, but for the sake of our listeners...
Yes.
For the listeners.
For the listeners. We do everything for the listeners. The Foucault pendulum is a tall pendulum.
It's a string with a bob.
In principle, you would have the support point essentially frictionless. And so then the plane of the oscillation of the pendulum is fixed in inertial space, but it's on a rotating platform. So if you're standing on the rotating platform, aka
the
planet Earth, then you would see that plane rotate over time.
So like the way it's usually demonstrated is, so you like if you just looked at it and you were in the same inertial frame, it would just go back and forth, basically. But like it's usually that you have the pendulum set up and then like little dominoes set up in a circle around it, and over the course of the day, it knocks down almost all the dominoes.
Yeah. So you can imagine the simple-minded view, which is what I had, is imagine it's over the North Pole, right? So it's oscillating in an inertial thing, and the Earth is rotating underneath it in 24 hours. So over the course of 24 hours, if you were standing there at the North Pole, you would see the pendulum's oscillations rotate around through a full cycle in 24 hours. So it proves the rotation of the Earth. And that's why it was invented.
Really cool.
Yeah.
And it worked. But it turns out that the period of the rotation of that plane depends on your latitude. If you're on the equator, it doesn't oscillate.
So
it doesn't rotate, I should say, right?
Yeah.
And if you're at the North Pole, it rotates once in 23 hours and 56 minutes, right?
So if you're in between,
it goes as the sine or 1 over the cosine or something in the latitude.
Yeah.
So
because
that's really cool.
Yeah.
Because
spheres, and I want Jim's flat Earth model to account for that.
Yeah, Jim, if you're watching, listening.
See if that can happen or not, and I don't think so.
I don't think it can.
I think he's bluffing.
What?
Yes.
No.
I'm throwing it down,
All right.
top quark. I
Make
want to
us-
see this flat Earth model.
With your Foucault pendulum.
Yeah.
Anyway, you
Speak-
know what else
yeah.
is different at the equator? Or is
Yeah.
launches. That's part of the reason we launch near.
Oh.
It's not really, but part of the reason
Yeah.
we say we launch near the equator is 'cause it's rotating a little
Faster.
bit faster.
Yeah.
So you get some
That's a good
extra
reason.
energy,
kick.
Yeah.
some extra kick.
We had a few of those.
We had a few of those this week. There was some here in Florida and some in California.
Right. More Starlinks have gone up,
Of course.
We had
We've-
people go up.
and people.
People-
Crew
Oh, no.
5.
Yeah, on a SpaceX Dragon
Mhm.
capsule. They're on the ISS now.
Yeah, they're boarded.
It was 2 U.S. astronauts, one
Japanese.
astronaut, and 1 Russian cosmonaut, which is the first time they've flown on the SpaceX.
Wow.
Yeah.
So that was interesting.
And
timing.
so, are some crew coming down from ISS?
Yes. There was
Uh,
actually just another launch a few weeks ago from Russia with a U.S. crew person and 2 Russian crew people.
Okay.
And so there are some more folks coming back.
Are
though. This
all
was delayed, I
four-
think.
Are all 4 of the crew 5 people staying up there for a long period, or are some of them just like, I'm
They're
just
all
here for a
staying
couple
for a
weeks?
few months at least.
So they're not
Yes.
like one of these visiting.
Sometimes it's like,
None of them are just short-term visiting.
Okay.
I think
okay,
it's true.
so there will be a serious turnover of
Yeah.
the residents
I believe that's
of
true.
the ISS.
Yeah.
Okay.
Which is exciting.
Yeah.
And they.
When is? Do you know when that Crew Dragon thing is coming down?
So that's. I don't know if it's. I think it's several months.
Oh, really?
Yeah,
Okay.
I think.
I still sort of have in my mind the pattern in the shuttle days, when the shuttle would go up with 7 people, they would like
Yeah.
drop off 3,
Yes.
pick up 3, and they would only be there for a week or
Right.
10 days or something like that, just because the duration of the shuttle missions.
I think
was
I think with
limited.
the SpaceX Dragon missions, I think the same so far. I think the same people who go up come back down on the Dragon.
Okay. Oh, okay. Interesting. Okay, so they're not. I got it. So the Crew Dragon's just going to hang out there and do its thing
Yeah.
with its people until they come home. Well, we had other space. I guess I don't know if this is now. It was space news before, but now it's science news. The
D.A.R.T?
The dartboard.
Yeah,
The
so
dartboard.
last time we recorded, D.A.R.T was about to strike. So this spacecraft hitting one of these moons of, was it
It hit the moon of
Diddy Moon.
Didymos.
as we like
Diddy
to call it?
Moon.
Diddy Moon.
Diddy
Or
Moon.
Dimorphos.
Dimorphos.
But we like Diddy Moon. Yeah, so we've had some images now, actually images from everywhere. So we've got images from the actual impactor itself as it was approaching the moon.
And
And
yeah, some pretty nice
they were
close-up
really cool.
images. I was surprised at how
Nice they were.
What a nice close-in, high-resolution view we got, because it's screaming into the surface of that asteroid at something, I don't remember the number, but more than 10,000 miles per hour. I don't remember what that is in real units, but more than 10 kilometers per second.
And so it was able to get very crisp.
So yeah, when you're close enough to get a crisp picture, it means you're also instants away from being obliterated. So
Right.
to get the picture back quickly was cool.
Yeah.
And
So
where are the other pictures from?
we've got other pictures from. They set up. Anyone who could was told to basically
Yeah.
Take a look.
point your
Point
telescopes in that direction,
Yeah.
and they've been the one team has been able to see the trail that's been left behind from this impact, and I'm just trying to get the number here. It's 10,000 kilometers long. This tail behind.
Okay,
Debris
and
tail.
getting
Debris tail.
longer,
And getting longer.
presumably.
Yeah.
Yeah.
So that's really cool. That's ground-based telescopes doing that, and then we also have the images from the Licia cube, which is the little Italian CubeSat
Right.
Yep.
that was in the holster of the the larger spacecraft, that basically just kind of took a back seat and watched the impending doom. And
Yeah.
took some images, and they had 2 cameras, Luke and Leia. One of them colour images and one of them black and white. And just seeing this impact. So now we've got these images through, and they've shared them really quickly. But now we just need to start. I say we. The teams involved are going to start processing that data and trying to understand. Is the debris cloud the kind of size that we were expecting, and has the Has the moon been shifted? Has its orbit shifted? I think they're trying to change it by like 10 minutes or something.
The period?
The period of the...
Out of how many?
I think it was like 1%.
Yeah, I think
something like that.
Yeah.
Right.
So lots of number crunching to come, but the images are great.
And what's the size of Dimorphos?
Very small.
Again?
Yes.
Okay. And so, and it's just worth reminding, so first, as has been said, I think appropriately in all the coverage that I've seen of this,
Dimorphos is,
that this moon of an asteroid and the asteroid itself were never and will never be an impact threat to the Earth.
Yes.
We only hit it to see, can we hit something, and can we then see that it is now on a slightly different path.
Yeah, basically. And we didn't even hit the primary body, we hit the moon.
Right.
So.
We hit the smaller, and that's what exactly I was getting to, is that if you hit a single body orbiting the sun, then you've got to figure out how its orbit around the sun changed, which is a little bit tougher than this, because now they're checking the orbit of Dimorphos around the bigger asteroid. And as you were saying, Hannah, they can do that just by how long does it take to go around. And since it's not taking years to go around, you can imagine if it were a 1% change, and first you wouldn't be able to make a 1% change in the orbital period of an asteroid going around the sun.
Yeah, you'd need a lot more
energy
to do that.
That would be a much bigger ask than what D.A.R.T was able to deliver. But it could make a 1% change in the orbit of this little tiny rock around the slightly bigger rock, and since that orbital period is days probably, then you just measure it for a few weeks, and then you see, oh, okay, yes, the period is now a different number. And they're not really looking at, can I see a difference in the path of this thing? It's, I know that the path determines the time to go around, and I can measure the time to go around. That's an easier measurement to make than seeing its trace across the sky.
Yeah, and I guess the main thing that they're trying to do is see if what they thought would happen did happen. Because then if we do need to perform an actual real-life asteroid redirect mission, that the calculations that are in place, we know this is tried and tested, and our predictions will probably play out. So if it doesn't behave as we expect, then we need to understand why, for future impending doom, basically.
Yeah, and it was very rubble pile-y, so it's a very interesting, because I think we talked about this a little bit before, that like if it's very loosely structured, that can absorb a lot of the energy differently than like
in a solid rocky body.
Rocky body. So
that's the throw the lump of clay at the door instead of throw the bouncy ball at the door.
Yeah, and it did end up being very
lump of clay,
crumbly,
probably,
like that cornbread.
So, so I think that would argue that it's probably what?
It was so cool.
That it's probably not going to have made as big a momentum change in that orbit as it maybe could have if it were less rubble pile-y.
Although it did lose a lot of, it seems like it's lost a lot of
material.
Right,
So.
And that carries
turns out low gravity, hard to hold on to.
It is so hard to hold on to stuff. Yeah. Well, and do we have any other space news? Anything from the JWST?
There's new images of Europa from the Juno spacecraft.
Orbiting Jupiter. And so these were like super close flyby images of Europa. I don't remember how close.
I'm just looking at one now. It looks like a giant ear on the...
A giant ear on Europa.
A giant ear on Europa.
So Europa is an icy moon of Jupiter. And the last really high resolution images we had were Galileo.
Right.
Like all the images we look at of all the icy moons have been these images from many years ago.
Yeah.
That are from Galileo. And so
and Galileo was not able to get the number and the quality that it should have been able to get, and that we hoped it would be able to get, because it had this famous failure of its high gain antenna. Which was like an umbrella that unfurled.
But it was like an umbrella in a storm, it turned out.
Thank goodness Cassini's launched with a fully unfurled umbrella. But Galileo's didn't, and that cut the data rate by a factor of 1,000. So they only got a handful of pictures, and now Juno, which this is not its primary mission, but is there.
But it was flying by. It's
got there's an image here. It says taken at about 250 miles.
That's what I was going to say. Yeah, it
Nice and
was
close.
crazy
That's,
close.
yeah, it's really good.
So Juno's in its extended mission, and it's on this really big orbit, but it's got super close, and it took these fascinating images of some of the really chaotic terrain on Europa.
And
Yeah.
Europa's a really hot topic, right? Like those icy moons are really.
Well, we're
there's a lot of
building
interest.
the Europa Clipper mission, which will be designed specifically to study Europa. Sadly, it's not a Europa orbiter or lander. It's still a Jupiter orbiter, but its orbit around Jupiter is tied to Europa's orbit. So it'll be making
Like a
lots and
flybys.
lots and lots and lots of very close flybys like this.
Yeah.
Whereas Juno is on these big 2-month
Big
orbits
old
to
loop.
dive in close
Nice.
to Jupiter, happened to come close to Europa this time,
Yeah.
which is awesome. Europa it's a weird looking moon.
It's so weird. It's all cracked. So it's icy, and so it's all cracky, and it's got all these weird features that look like they're cracks from different times, and it looks like things that are maybe crater features, and it's
some of the
pretty
cracks
cool.
have these sort of interesting like cycloidal like patterns to it that is probably related to the tidal interaction between the moon and the planet that causes periodic stresses
Yeah.
Right, on different
that
sides.
sort of rotate around the moon over time.
Yeah.
So it's one of these weird looking moons like
Yeah.
Enceladus and like shoot.
The
I'm
other
blank
icy
Miranda.
moon.
I was thinking of
Miranda.
it at Uranus, which is a
Well,
weird
but-
looking
yeah.
moon.
It says here that the images were taken by JunoCam and described as the outstanding public outreach camera. So was it purely just
Yes.
for outreach? It was like an
Yeah.
addition, right?
So the original Juno mission did not have a visible light camera at all. Any cameras. It's mostly studying like magnetosphere and particle stuff.
And the internal structure of the planet, which
is
it
gravity.
gets basically just from Doppler tracking of the spacecraft.
Yeah. So like we were talking about
Radio
with D.A.R.T,
tracking
like
of spacecraft,
figuring out
yeah.
how gravity is affecting the
Right,
structure, right?
that's right.
The orbit. But so they get these images and they almost immediately go up on a website, and like a lot of the images you'll see on the web are from citizen scientists that like go on and process the data and do cool
and
things.
do
with
amazing
it.
things,
Yeah, I think there's like now that's become
There's, like,
a
good
thing
pipelines,
out there.
yeah,
like there's
for sure.
All of these images, not just from Juno, but
Yeah.
we're seeing this with JWST images as well, is that people are taking the raw images and doing some, processing to make them more visually accessible, I guess.
Yeah.
So it's not like science processing, but it's like lets everybody get a nice, good look early at these pictures, which is really cool.
Yeah.
Yeah.
That's super cool. And then speaking of impacts,
Yes.
we have a little bit more sciencey topic.
Okay. Which one?
Mercury.
Yes.
Speaking of
I totally know what's going on here.
speaking of planetary surfaces with lots of lines and cracks and craters.
Let
and
me
odd things happening.
let me give you your trivia first.
Okay.
Because it's a little
Your
bit
trivia today is, what are we talking about?
That's
Nobody knows.
I knew we were talking about Mercury, but I'm sorry.
It's fine.
The segue.
My segue wasn't as clean as you would have liked.
Nobel Prizes were announced this week, as we have
Should I
alluded
have read
Missed
up on
out
this?
again.
to.
Yep.
So the main trivia
Okay.
is one of the winners
Okay.
was unusual in a particular way, and it's multiple choice.
Okay.
So you're gonna have
Of
to tell me.
any of the Nobel Prizes we're talking
Yes.
about. Okay.
Yes. One of the Nobel Prize winners that was announced this week
Okay.
had an unusual characteristic. What was that unusual characteristic? And here are your four choices. Okay? So it's
Okay.
not bad.
Okay.
The winner was from a country who had never previously had a Nobel laureate.
Okay.
It was the youngest winner of a non-peace Nobel Prize.
Okay.
It was the oldest winner of a Nobel Prize. They're never given posthumously, so
Yeah.
you gotta
Yeah.
be alive
Right.
Yeah.
to get a Nobel Prize.
Yeah.
Or it was a winner who had previously won this same Nobel Prize. So one of those things is true about one of the Nobel Prize winners from this week. After we come back to the answer, there will be a follow-up.
What?
Yes.
Oh man.
Yeah. Okay.
Shocking.
So
Okay,
now
so-
Mercury.
What about Mercury?
It's getting hit like a lot.
Maybe.
Maybe.
We don't. So there, we talked about Mercury recently.
With
It's
ice.
been-
Yes.
That's right, about icy Mercury. So I'm not sure if there was like a special issue or something, but there's been a bunch of Mercury stuff coming out recently. Part of it is there's the Bepi-Colombo mission that will be coming online around Mercury.
It's going to be a while, but it's had a recent second flyby
Yeah.
as part of it, like trying to get to
couple more
orbit.
years or
Yeah.
something.
I
but-
mean, but it's
on
its
its
way.
way.
status normal.
Yes.
Nothing.
Yeah.
No
Yeah.
anomalies. It's just doing
But
these
it's getting there
many,
and
many loops around the sun, trying to burn off energy so that it
To
can
slow down to
enough
Mercury.
to go into orbit around Mercury.
yeah, but it means that everyone's kind of getting pumped about Mercury right now.
Okay.
Because
Yeah.
It's Mercury's
It's coming
moment to
soon.
shine.
And in the meantime, we're still analyzing data from previous Mercury mission
Like
called
Messenger.
Messenger. So Messenger was a U.S. mission, and Messenger is an acronym
yeah.
that I'm just going to say.
Yes, it is.
That orbited Mercury from 2011 to 2015, and it has a lot of really good high-resolution imagery. So kind of like what we were just talking about with Europa, we got all this amazing high-resolution imagery of the surface. And not only is it high-resolution, but they often, if you're orbiting for 4 years, you get repeat coverage at the same locations, but often with different lighting, stuff like
Right.
that. So you can use it to do stereo imaging and figure out topography, but you can also use it to look for changes over time. And so there's a new paper that came out that examined over 58,000 pairs of messenger images. With, I hope with some sort of
Right.
image analysis algorithm.
So I was
It's just,
about to
it's just
say.
a bunch of people with magnifying glasses.
I mean,
think.
that's, yeah, right. That had overlapping regions, right? So it imaged the same region at different times. But actually, these all had similar photometric angles, so similar lighting and imaging angles,
Okay.
so that you weren't getting big contrasts
That-
in imaging that would
make
like
some things pop out
Yeah.
in some views, but not in others.
Yeah, because that's actually one of the challenges when you are doing automated image analysis. If you're
It's
trying to look for
so
something that's
hard.
bright in one image and changes, but like maybe it's just dark in the other image because your lighting's completely different.
So there's a big sub industry in our field
Mm-hmm.
of astronomy that is around counting craters
Yeah.
to figure out the
Yeah, there
size
is.
distribution of craters on asteroids, moons, planets. How many craters are there between, of each size, and how worn down are those craters, all sorts of characteristics of them. And I have to say, every time I read a paper about it or look at the pictures of those things or see that stuff, my I don't know what the right metaphor is. My eyes glaze over, my head swims, all sorts of strange things are happening because I cannot wrap my head around that task
Yeah.
of counting
And that's the
and
thing.
identifying those craters.
Because they're
People love
getting
it.
really good at, but they are
Some
getting really
people love
good
it.
at developing these automated
Yeah.
programs now, and they're being used for a lot of this type of vast processing.
Yeah,
can, but there's still a lot of it that's,
it's
like,
a
just
lot of it
hard.
is individual people making a decision and clicking on a with a mouse and click on a thing.
And that's where a lot of the citizen science project comes in.
I was gonna say,
Yeah.
It
so
is.
some of them are, and that
To,
is because,
validate
and the
it.
reason they do that a lot of times with citizen science is because your computer algorithms haven't caught it the first time, or to train. Now it's a little bit more to train computer and
Yeah.
AI stuff like that, But so this one, they did do a lot of the processing with different calibration routines and combining routines, but then they produced GIFs showing the blinking before and after images,
Yes.
and then searched through those.
Right.
So
yeah.
it was probably less than the 58,000, but it was still a lot of GIFs to look through. And so the interesting result is that they found a bunch of changes. So they found approximately 20 features that they discuss in this paper
that appeared during this very
four
astronomically
years.
brief period of time.
Yeah.
19
on Mercury. 19 quasi-circular surface changes and 1 linear feature. And they're mostly in the northern hemisphere, but that's probably an imaging bias kind of thing. There's a
Okay.
few in the southern hemisphere. And so these are all changes that are sort of circular, so that means maybe like a cratering feature. So if you take that as an impactor origin, impactor for this sort of size thing, it means that something like 1,000 times the previously estimated cratering rate.
So in other words, they saw 20, they were expecting to see 0.02 or something like that.
Yeah.
So that means either
That are of this size. That
Yeah.
they
Right,
imaging,
yeah.
So that means that all of the calculations that have ever been done and all inferred aging from crater counting is wrong, or there's another explanation.
Exactly, yeah.
Something different is going on in your solar system right now, for example, would be one possibility.
Sure, yeah. Maybe there's like, maybe for some reason there was some sort of extra impact. But, go ahead.
No, I was just going to say, I mean, there's been for a while people, are sort of searching in the inner solar system for other populations of objects, like is there sort of hidden belt or population of asteroids that are in close in the Mercury region.
What are those called?
Vulcans,
that's right.
And of course they're very hard to see because you have to look very close towards the sun to see them, and since they're close to the sun, the daylight side of them that would be reflecting light back to you is facing the sun or washed out in the sun's light, so it's difficult to see them. But so that's been just an area of research, is like trying to track down. It's hard, so maybe this is a clue.
Sure. The other option is that it's not external or exogenous, but it's endogenous, internal origins.
Local.
And so Mercury is generally a pretty volcanically and geologically dead body, but there are some changes that we see that are still from it cooling down, are still from changes on the surface.
That's incredible.
And so one of the craters, or one of the features they see, looks like it has rays. So like impactors often produce fresh rays on it. So they think that one maybe is an impactor. But the others could be these things called hollows, which are sort of rounded depressions with sharp rims that they've seen
Something
previously.
Collapsed or something?
Yeah, so they've seen in various different places on the surface, and they're often in really low reflectance parts of the surfaces, so they're hard to see. And they sort of have like bubbly shapes sometimes, and they are like these. Anyway, they have like sort of strange shapes, but they may be due to like volatile loss. So we talked about ices on Mercury last time. They could be due to like volatiles coming up out and like removing.
So that's kind of the best of both worlds, because on the one hand, even if only one of them is a crater, that's still 50 times more than they were expecting to see.
Or just like really lucky, right?
Yeah, that's just plus or minus one crater. That's
true.
Yeah.
That's acceptable.
Okay.
But if they are endogenous features, or things that are changing due to tectonics, not tectonics, but surface faulting and things like that, or volatilization, they show that the surface is changing.
Yeah, which
Mercury.
is certainly not something we think about when we think of Mercury.
No.
As I know all of our listeners, when they think about Mercury, they think like we do, that place, nothing is dead.
It's dead. It's the same as it always was.
It's like a small town.
It hasn't changed in a long time.
After midnight, it's dead. Not a lot going on.
So this makes the upcoming Bepi Colombo mission even more timely.
Yeah, because you're going to be extending that. You'll be able to look at these same regions again first, and then you'll be having another extended time period.
And they can focus on certain regions, And they say, so if these 20 features is, the alteration rate we're seeing with these 20 features is consistent with, has been happening over a long time, 99% of the planet's surface could change in the next 25 million years, which, again, that doesn't
blink
sound
of an eye.
That sounds really long, right? But on a geologic time scale, when we're sort of expecting this to be a fairly stagnant surface, that's a huge difference.
Yeah, in fact, in class yesterday, I think we were just saying how Mercury's surface doesn't change, but apparently it does.
Right. Yeah,
I have to update those slides.
I know. Sorry, class, we have an update
students.
to some errata to the previous lecture.
Well, our final topic is jumping out to the astrophysical, beyond the solar system and beyond our galaxy, and well beyond our galaxy to the early days of the universe. And it has to do with the search for population 3 stars.
Pop 3.
Tell me more.
Well, contrary to what their name might suggest, population 3 stars would be the first stars.
This is the thing I hate.
Astronomers.
Came up with, I know. So astronomers are really bad about doing backwards numbering and naming conventions and stuff like that. But who decided this was a good idea?
I know. Well, they seem to be, I think, very traditional, because what happens is they came up with, they see like two different things, and they don't know what the difference is due to.
Sure.
So they just say, this is type 1 and this is type 2.
Yeah.
And that they did that with stars. Then it turns out that the difference between them was the type 2s came before the type 1s.
Yeah.
So they, that was a flip of a coin, they got unlucky. So then it turns out, but the type 2s were not the first stars.
Nope.
Something had to come before the type 2s. So instead of just like saying, you know what, let's start
again,
over
right?
and
Clean slate.
no, they're just like, we're
Dig the heels
sticking
in.
with it. So whatever came before type 2, if type 1 came after, it must be type 3 came before. So population 3 is the
Pop
original population of stars, and the difference between these populations is stars make heavier elements out of light elements through nuclear synthesis, and then they blow up and they send all those heavier elements out into the cosmos, which then become part of new stars.
Yes.
So the later the generation of stars, the higher their so-called metallicity, which is the abundance of non-hydrogen, non-helium
So they've
elements.
got heavier things.
Heavier than
heavier things.
hydrogen
They've got
and helium.
Yeah.
heavier elements in them. So the population 3 stars is the population of stars that formed when there had not been any other explosions of
OG
stars.
Yeah,
Yeah.
from the
Your
original hydrogen.
Your OG stars, just your
OH.
original Big Bang
Yes.
Yeah.
stuff.
Yeah.
And so there's some very interesting things about that, is when you don't have any of those heavier elements in your star, when it's really just a very, what they call low metallicity, very pure hydrogen and helium star, first, it can get pretty damn big.
Yeah.
So
They're going to be really big stars.
hundreds of times the mass of the sun.
They're going to be like Beyonce. Really big stars.
Oh.
I was
Not
like,
massive.
right, that's what.
Sorry.
I was like, bold choice.
Not in terms of mass, in terms of
Sorry, Queen Bee.
star.
Magnitude.
Yes, magnitude,
Yes.
exactly.
Although because astronomers are backwards,
That's
the
true,
magnitude would be a
shoot.
very small number.
Yes.
A very big negative number.
I retract my confusing.
I liked it.
Thank
anyway, so they can be hundreds of times the mass of the sun, up to maybe 300 times the mass of the sun, and they can't blow up in the usual way that your population 2 and population 1 stars blow up. The supernova that they produce goes through a different process, which is called a what's it called? A pair instability supernova. So this is pretty cool, and we've talked about this on
You
some
look really
ancient
excited.
episode because people have been looking for evidence of pair instability supernova, and it's hard to find
Yeah.
because a regular supernova leaves behind a neutron star, and you can see those, or a black hole, and you can see the surroundings and the evidence for a black hole. But a pair instability supernova, it's a complete, there's no thing there left. All the stuff goes out into the cosmos, just this debris.
Right.
And the way that, a star's basic functioning is gravity is trying to make it collapse, and the nuclear reactions are producing high energy photons that provide pressure that fight that collapse, and it lives in this balance.
Yeah.
And it lives in that balance until it can't make those high energy photons anymore. It runs out of fuel, and then it collapses, and that's your supernova. Well, the POP3 supernova, what happens is those high energy photons end up interacting with the nuclei of the atoms in the star and producing electron-positron pairs. And so that essentially absorbs those gamma rays that would normally be supporting the star,
Right.
and that absorption, that reduction in that gamma ray pressure allows the star to collapse some. When it does, that heats up the reaction, so you produce more gamma rays, etc. But at some point, you can blow up. And this was super confusing to me because what happens when you have a positron and an electron?
They annihilate.
They annihilate and they produce 2 gamma rays, which you would say, oh, okay, that should help support
Increasing
it.
the...
Right, yes,
Yeah.
increasing the pressure and keep it up. But as it happens, do the numbers, pull out your
do the
calculator,
numbers.
pull out
Yeah.
your slide rule and your napkin, and you figure it out that the positron-electron annihilation rate is not enough to keep up with this absorption and this collapse, so the whole
Okay.
thing just blows.
Just goes boom.
And how do you then...
Just like your mind.
blows my mind. So then how do you see the traces of it? You see the traces of it because POP3 is not 100% hydrogen and helium and lithium. It's got,
which is good because like those elements, it's harder to find observable lines.
Yeah.
So we look at these with different types of spectra and all different wavelengths. It's just a lot harder to like find lines to look at that we can find.
So it has little bits of this, what astronomers like to call metals, but at a much, much reduced abundance, and the ratio of, in particular, iron and magnesium is very much lower in the POP3 than in the POP2. And they think they've picked that up spectroscopically around a very, very distant quasar, which also ties in with it being POP3, because very distant means very young universe.
Yes.
Right.
Distant,
So
like 7.5, a redshift, Z equals 7.5.
So I said, okay, we know that's a big number, right, for the
That's a big
redshift number.
Yes.
That has to do with sort of like the multiplicative factor by which the universe has expanded since that time.
So it's
So I said, but let's get that. What's that in light years? So I put it into. I googled a Z to light year calculator, and it said 103 billion light years.
It's a little bit off. Maybe it's a really
like,
old star.
Well, I had to count the digits, so I was like, wait a minute, that doesn't make any
right.
sense.
I was like, what kind of, is that a US billion or a UK billion?
Oh, there you go. Maybe that's the problem. Maybe that was the problem.
I was like hundreds, thousands. Anyway,
That's ridiculous.
I found a better calculator.
Okay, good.
And it's.
I didn't know. That's not a thing you'd think is like you. Like, is this calculator just off by probably?
Yeah. Well, that's the internet for you.
That's
you have to
true.
Check your sources. So it turns out that's from a distance of about 13 billion light year light travel time, or when the universe was about 700 million years old. So a baby universe.
Which makes sense for POP3 because then that would be the early first
before
stars.
you had all these generations of stars making new stars out of the debris or the explosions from prior
G-rated
generations
podcast.
of stars. Yeah. So anyway, this paper that just came out in the Astrophysical Journal by Yoshi and co-authors just this month says they say this is the sort of strongest evidence for a parent stability supernova with this very distant location.
Yeah, and it's interesting. So the observations were in, I don't know, I think near infrared. It was a spectrometer, and they have these observations. And like one of the like fascinating things. Near infrared. So yeah, one of the fascinating things about like this work is that like we've looked at these wavelengths and we've looked at these objects before, but this is another one of those cases of how you process the data. And what you subtract out and what systematic changes you think happen in the universe that modify the signal you're seeing. And so like it's a really so they get this like weirdly low ratio, but it's like an analysis that we haven't been able to do before because some of the other things we assumed were like noise sources or other contamination sources like said, oh, there's no signal there. But they said, wait, what if we process it this way? And then there was a signal there. Yeah.
So they didn't just like get their binoculars out and look at this thing.
There it is.
And there was a number that said iron equals 0.1 and magnesium equals 19 or whatever. Yeah, it's hard work to pull that stuff out, but that's a pretty cool discovery. So maybe they'll get a Nobel Prize someday.
Maybe.
And
not if I get there first.
We'll get in the write-up.
So, for your Nobel trivia.
Okay.
What was unusual about one of this year's Nobel Prize winners announced this week? The winner was from a country who had never previously had a Nobel laureate. It was the youngest winner, excluding Peace Prize. I'm doing that because of just Malala won the Nobel Peace Prize. She's the youngest, 17 years old. It was the oldest winner of Nobel Prize, or it's somebody who had previously won the same Nobel Prize.
I'm going to go A. Different country.
New country represented in the pantheon of Nobel laureates.
Yeah, I agree.
Actually, it is somebody who had previously won the Nobel Prize.
Different in the same category?
Yes.
I thought you couldn't.
Wow.
You can. Yes, which is going to be
Einstein.
No.
No, his were different
He
categories.
only won once.
Oh, that's right.
Yeah.
Was it Marie Curie who won different?
She won
different
Well, hang on,
physics?
because this is your second follow-up question, you guys.
We're jumping
Hang on.
the shark.
How many individuals have won the Nobel Prize more than once?
Okay, at least one.
Yeah, at least I'm going to say
Including this person.
including this person. I'm going
Yeah.
to say 5.
3.
It is exactly 5.
Wow.
Oh,
Yeah.
that's a good stab in the dark.
Yeah.
I mean, I knew
Now,
that.
Of the dual winners, 4 of the 5 had at least one of their wins in which category?
Oh gosh.
And your categories, there's like physiology / medicine is one, literature, peace, chemistry,
What
physics.
I'm just supposed to pick one.
I'm going to
Yeah.
go chemistry.
You're saying chemistry?
Mm-hmm.
Say it again. What's the?
What are they?
No. What am I? Which?
4 of the 5 dual winners had at least one of their prizes in one of those categories.
Medicine.
It's actually chemistry.
I thought it was.
Yeah, including this year.
Dimorphos.
So this year's winner, Barry Sharpless,
That's just an unfortunate name.
yeah, shared the 2022 Nobel Prize in Chemistry. He previously shared the award in chemistry in 2001.
Oh.
Well,
What,
no.
your final
okay.
follow-up, what were the categories or category for the 5th double winner, the one who did not have chemistry?
Medicine and physics.
Medicine
I
and
don't
peace?
Physics
Oh, I like that.
and physics. John Bardeen.
Ah.
Oh, I see.
Transistors
It could be the same category. That
and
makes sense.
superconductivity.
Stumped.
Yeah. Man, that guy should have done more.
Yeah, just a couple of trivial things like transistors and
and
superconductivity.
superconductivity. That's fine.
Right. I don't know if you knew Chuck Bardeen.
I didn't ever meet him.
Yeah, John
Yeah.
Bardeen's grandson
Yeah.
was a grad student at Colorado when I was there, and then he worked in atmospheric science, so he
Yeah.
worked very closely with a good friend of mine
Yeah.
in Colorado. And I talked to him about, he's like, yeah, when he won the first prize, nobody went with him because they didn't have any money. But it's like when he
Sure.
won the second one, at that point, the family got to go along for the awards. The other 3 double winners, so we have this year's double winner, Barry Sharpless, who previously won in chemistry, John Bardeen twice in physics. The other 3 are Mary Curie.
Uh-huh.
Hers were in physics and chemistry.
Yep.
Linus Pauling,
Oh.
who was the only person to win it twice by himself.
Mm.
Once in chemistry, of course, as we know, and the other in peace.
Oh.
And Frederick Sanger, another 2-time chemistry winner.
Those chemists,
so
man.
go
Yeah.
into chemistry.
Yeah, I was gonna say,
if you want
go
your
into
set-
chemistry.
Yeah,
Is it
they
still
got a
time to
shortage.
re-specialize?
It's like they got so many Nobel Prizes, they're just giving them to the same people over and over again.
Can I
there.
say that my work is in chemistry?
Say it.
Totally.
Yes.
It is now.
It is
Nobels-
now.
That's why we probably should have nominated
We
ourselves in
should have.
chemistry.
We should
Mm.
have.
I mean,
yeah.
nominated each
I
other.
went for
Yes,
literature.
of course.
Yeah.
Oh yeah, that's a good call.
While it may have felt like waiting for a Foucault pendulum to make a complete rotational cycle, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel and catch up on old episodes wherever you get your podcasts. Follow us on Twitter
At walk_the_galaxy.
and ask us questions anywhere using hashtag AskWG or email wgg at ucf.edu. Our theme music was composed by Richard Perusik. Production assistance is provided by Logan Basinger. Production is underway on our second music video. Thank you very much. Thanks to our listeners in Queensland, Australia, and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Hannah Sargent.
We're the AstroQuarks signing off until the next episode of Walkabout the Galaxy.
Nobel.